Hey, all, this is Derek, and we're starting off Chapter 5, which is going to be about quadratic functions primarily. But before we get to do quadratics, we got to look at a new version of numbers that we haven't looked at least in this course, which is complex numbers. And quadratics we're going to see are kind of those U-shaped parabolas. You may have seen them in a previous course. You probably did see them in a previous course. And if I draw a parabola, I can make it equal 0 twice. I can have two x-intercepts there, two solutions. If I draw it really careful, I can have it come down and just kind of bounce off and have one solution. So these are like two real solutions. This would be one real solution. But I could also draw a parabola that doesn't have real solutions. But that doesn't mean that when I go to solve that, it'd been better if I had drawn it right there, pretend that one. When I go to solve something like that, I get kind of a weird thing, which is when I bring this 4 over, I have something squared equals a negative, and that can't happen. And so all along we've been saying this doesn't have solutions. When I look here in the real plane, it doesn't have solutions. And what our first topic is, complex numbers, is how we're going to handle this issue right here, which is we're going to define a new number. And that number is going to be the imaginary number I. And it is that whenever we run into a root -1, we're going to call that I. Much in the same way when we see 3.14, yada, yada, that number that, is the ratio of the circumference to diameter of a circle, pi. So we call that pi because it's convenient. We're calling this I for imaginary unit this because it's convenient. And it's easier to write this than it is to write that. And then I squared is defined as -1. So these are our two definitions. I is the square root of -1. I squared is -1. Okay, and then the rest of the section is pretty much operations with complex numbers, which is pretty straightforward, it turns out. So first let's look at standard form for a complex number. And it's going to be this a plus bi. And A is called the real part. So all the numbers like 1, 2, 3, 4, 5, 6, 7 that we've known for all our lives, that's A. And then B is called the imaginary part, and that's where we're going to get this imaginary value I here. If B is 0, then A is a real number. That's what I was just saying. That's our numbers that we know and love. If A is 0, then BI is an imaginary number, and then together they make a complex number. So perform indicated operations, simplify, and then make sure our answer is in standard form. This is that standard form. So we're always trying to get to here when we're simplifying. And that said, there's a little bit of answer entry stuff, and we'll see some answers with fractions, but I'll show you that when we get there. So this first one is addition, and complex numbers do pretty much exactly what you would guess. They work just like terms. So if you kind of do whatever you're like, I think I would just do this, that's generally pretty much right with these. So this is our first complex number. These parentheses are just kind of showing it's two complex numbers, but math-wise, they're not really doing much there. So I'm going to write it without, and I'm going to go 4 minus 7i plus -5 is really just -5, plus -2i is really just -2i. It'll matter when it's a minus. And now I would add the real parts together and the imaginary parts together, and that's it. So 4 minus 5 is -1, and then -7i minus 2i is -9i. So you can really just think of it as collecting like terms, and that's exactly what you would think to do. This next one, so this is subtracting two complex numbers, and the same way that if this was 6 minus 7x, we would have to distribute that negative. It's exact same. So we'll rewrite this as -4 plus 2i minus 6 minus negative makes plus 7i. And now we'll just kind of collect up our like terms here. So this will be -10, 2 and 7 for 9i. Okay, for this next round, we are multiplying. And so much as you would do if this said -6x times 2x, it's basically the same idea. The -6 times 2 would make a -12. In the same way, x times x would be x squared. I times I is I squared. But then remember, I squared is -1. So every time we see an I squared, we have a little bit more work to do because we're not in standard form, which is A plus B I, no squareds on our I's. So this means we need to simplify where that's a -1, and now negative and negative flips that sign, and it becomes positive 12. So we'll see a lot of that as we do multiplication. This next one, we're going 3i times 4, so 3 times 4 would be 12, and then I comes along. Again, if you think of what you would do if it was an x, it's the exact same stuff. And then 3 times 5, so that'll be a minus 15i times I for I squared. And then this is really 12i minus 15, and that's a -1. So that's going to make 12i plus 15, which is right, but we should probably write it in the right order. So 15 plus 12i is the fully proper answer. This next one, so if it kind of makes you think FOIL, that's exactly right. That's what you do with it. So we'll just do out our steps. So we'll go 1 times 5 is 5. And on the outside, we're going 1 times 2i. And that is 2i. And then same thing with the inside last. So -3 times 5 for -15i. And -3 times 2 for -6. And then I squared. So this will be 5. 2 minus 15 is minus 13i, and then I squared there, so remember this is our -1, so it's going to flip that sign, which is what the I squared always does, is reverses the sign. So we'll make that a plus, and then 5 and 6 for 11, minus 13i. And now I'm in standard form, so that means I'm done. For this one, a couple of ways you can go. If you are good at doing perfect trinomial squares in your head, you can definitely do this out this way. Most people are not good at that. So I am going to show it as a FOIL. And then I will talk through how I would do the other version, because it's something that you would just do in your head. So let me do the FOIL first. 7 and 7, 49. On the outside, we're going to get a 14i. And then we'll get the same thing on the inside. And that's why the formula goes 2ab, is because we get 2 of these. And then on the ends, we get 2 times 2 for 4, and I squared. So when we have something of this form, it's going to go a squared plus 2ab plus b squared. So the other way I can do this is go 7 times 7, 49. 7 times 2 would be 14, and then double it with this 2 from the formula, so that'd be 28. And if you look, there's my 14 and 14 for 28. And then 2i times 2i, there's the 4i squared on the end. And this time it's that I squared, so I'm going to write that -1 as minus 4. And then collect my terms, 49 and 4, and that would be 45 plus 28i. So you can either do this or just do the FOIL, and it comes out the same. Okay, complex conjugates. So conjugates are things like a plus b, a minus b. So that's conjugate pairs. Complex conjugate pairs, same thing, except now with complex numbers. A plus b, I, a minus bi. So normally when we FOIL these, right, these would come out to a squared minus b squared. And this is our, our difference of squares formula going the other direction. This is that a squared plus b squared that never factored. It's because it involved these complex values. So here, when I do my bi times negative bi, I would get negative bi squared. And then remember how I squared is -1, oops, b squared, I squared, pardon me. And I squared is -1, so that's what ends up flipping that and changing it to the plus, is having those i's on the end versus the minus in this one. So anyhow, the short of it is, if you have complex conjugate pairs, you don't actually have to do out all the FOIL. You can just use this shortcut. So I will do the FOIL on this one just to show you why the shortcut works, and then I'll show you the shortcut afterwards. So here it is the long ways. 5 times 5 for 25. On the outside, we're going to get a minus 15i. On the inside, plus 15i, so that's where those always cancel, so that's why we don't need to do all that. And then here, we're getting our minus 9i squared. So then 25, and then 15i plus 15i, those drop out. I squared is -1, and then -1 times -9 makes plus 9. So that's our 5 squared plus 3 squared that I could have gotten from right here for a squared plus b squared, 5 squared, and then b is, notice b doesn't include I, b is just the number in front of I, which is 3. and we get the exact same thing. So it just lets you skip over some steps, which is handy when we do division in a second. And so this should be 34. This next one, I'm going to do the FOIL on this as well, and then I'll show you the shortcut because people often get the shortcut wrong on this. So 4 times 4 for 16. So far so good. On the outside we get plus 4i, on the inside we get minus 4i, so there's that canceling. And then here we get minus and plus, so that would be minus I squared. Those cancel. And then 16, and then minus, this is a negative 1, right? So minus a negative 1 would be plus 1. So there's our a squared plus b squared. The problem is people, instead of putting a 1 here, what I see people do a bunch is they'll go 4 squared, and they don't use the 1 in front of the I. They say plus I squared, which is then negative 1. It comes out 15, but it should be 17. So careful if you have one where it's just an I. B isn't I, B is the number in front of the I, which in this case is the invisible one. Okay, so what can we do with complex conjugate pairs? As it turns out, we can use them to divide. So if I have something like this, where I have 3 divided by a complex number, which I could think of it as 3, right, divided by a complex number, so it's division. How can I get this out of this denominator is sort of the idea. And if you remember the problems with the roots, where we're rationalizing denominators, where say I had 3 over square root 5 plus 2. Remember the trick to that was to go root 5 minus 2. We would use the conjugate. Whoops, should be like that. Root 5 minus 2. We would use the conjugate because that cleaned up the radical in the denominator. We're going to do the same thing. Let me write this a little bit bigger right here. But we're going to use the complex conjugate. And that's kind of what this is showing. So for this one, we have 4 minus 2i. So I would want to use its opposite, still positive 4, but plus 2i. And then you'll see when I FOIL this, if I FOILed it out, right, that's what we just did on the last page, it's going to come out a squared plus b squared. It's not going to involve an I in the denominator, and so will be in standard form. So 3 times 4 up top would be 12, and I'm distributing, and so then 3 times 2 will be 6i. And then in the denominator, I'm going to use that shortcut. So 4 squared plus 2 times 2, or 2 squared. So up top we got 12 plus 6i over 16, and 4 would be 20. But then we have the issue that much like any other fraction, these things can reduce. And if you notice a value that divides in everywhere, that means you can simplify it. And again, it's that if you can factor it, you can cancel and then you can simplify. So if you think of it as taking a 2 out of the numerator, I would have 6 plus 3i. And then think of it as factoring a 2 out of here, I'd have 2 times 10, and those cancel. So when I'm doing it for me, I don't write all that. I just kind of go, okay, 2 goes into 12, 6, 2 goes into 6, 3, 2 goes into 10, sorry, 2 goes into 20, 10. And so that's a lot kind of cleaner for writing it, but this is the how come you can do that. And a couple more examples of that. So for this one, it's a negative 3 minus 4i. It's still negative 3. We didn't change the sign on the first number last time, so we still don't, even if it's a negative. So this would be its conjugate. And then from there, very similar. So we would be going 6 times negative 3 for negative 18, and then times 4 for plus 24i. And then the denominator, it'll be negative 3 squared plus 4 squared. And that will be negative 18 plus 24i over, that would be 9 and 16, so 25. And that, if you look, there's nothing that goes into, here I could factor out a 3, but it doesn't do anything with the 25. I can't divide out a 5, and this one's the limiting, so we can't reduce it any further. This one, same basic idea, the numerator is just a little bit more complicated this time. So 3 plus 4i, so our conjugate's going to be 3 minus 4i. And so this time we're going to have to do a little bit of FOIL for the numerator. So 2 times 3 is going to be 6. Outside minus 8i, inside 3i. And last is minus 4i squared. And then downstairs I'll use the shortcut, so 3 squared plus 4 squared. And cleaning up the numerator, 6, let's see, 8 minus 3 is minus 5i. And then this is I squared, so remember that's our negative 1, which makes this turn into a plus 4 from that minus 4. And 9 and 16 would be 25. And then let's see, 6 and 4, so that's giving us 10 minus 5i over 25. So here's one where it reduces, and this is where I would say, like I said, I could factor the 5 out, and that's why this works. For me, it's easier just to go 5 goes into 10 twice, 5 goes into 5 once, so invisible 1, 5 goes into 25 5 times. And that seems like an easy way to think about it. Hey, all that was getting a little bit long, so I decided to make this into a 2-part video. So this will be part C, so all the stuff involving radicals will be in this part. So for here, what we're learning is first kind of how to simplify when we have these radicals. And basically what this is saying is if I have square root of negative b, instead of kind of using that square root negative 1 that's really awkward, again, we're just going to call that I and then say root b. So instead of having something like this negative square root of negative 7, to call attention to this, rather than saying it is the square root of negative 1, we're going to say I root 7. That's simple. For square root of 25, so square root of 25, or sorry, negative 25, square root of 25 is 5, and then we would still have that root negative 1 there, and again, we're just calling attention to that by saying I. If you think about where you would put the X, that's kind of where the I tends to go, and that said, sometimes books aren't consistent on that. For me, I usually put it after numbers, same I would write 5x, not x5, that would look weird. And I usually don't write square root 7 with an x after, because it's hard to tell if it's underneath the radical. So that's kind of the same reason for putting it in front this time. Here you'll see I'll end up putting it between after the number and kind of before the radical. So this is, first off, it's a negative because there's a negative sign out front. And then it's going to involve an I because there's a radical, a negative under the radical. And then for that 24, I am going to think of that as a 4 times a 6. And so square root of 4, that would bring out a 2. So I'll just throw that in front there. And then we leave behind root 6. So the same exact way you would reduce root 24, you know, break it into the 4 and the 6, take out the 2, leave the 6. Everything's the same, it just happened to be a negative number in front, and because of this negative underneath, every time we see that, right, we get that I notation. Okay, so we're about to head into the land of addition and subtraction, and multiplication. And when we have multiplication, something I need to call attention to. So say I have square root negative 1 times square root negative 1. So that could come out a couple of ways. If I go square root negative 1 times negative 1 and I use the AB property, that comes out root 1 and I get 1. But if I think of this as negative 1 to the 1/2 to the 1/2, then I have negative 1 to the 1, which is negative 1. So that's a problem that I can make this come out to 2 different answers. And the issue is with this property, A and B have to be greater than 0. So if we have problems like what's coming up with the negative under the root, we have to write it in that I notation first. And what that does is then makes A and B positive numbers, and then it's valid to do that math. So the key to these, get I out of the expression, or get it out of the negative under the radical into the I notation, and then you're safe to proceed. So for this first one, we've got square root negative 27 plus square root negative 12. And what I'm going to do is I'm going to rewrite that so I can see my perfect squares a little bit easier. So I'm going to think of it as a 9 times a 3 for that 27, because I like the 9 because it's going to work. 12, 4 goes into that. So that one I'll write as 4 times 3. And you can kind of see there's my like terms coming up. So square root of 9 would bring out a 3. And so it used to be this would just be 3 root 3. Now it's 3I root 3. That's the only difference, is now it has that complex part. And then here we are bringing out a 2I. And then the same way, if I have 3 of something plus 2 of something, I have 5 of those somethings. That's all that's going on. We're just collecting up our like terms. So I now have 5 I root 3s. This is the one where I was saying if you multiply first and make that a positive, you will come up with the right answer with the backward sign. So careful to simplify I first. So, there's a couple of ways to do it. Let's do this. This is better. I'm just going to write this as I root 18, and then I'm going to write this one as I root 8. And then if you go 18 times 8, well, actually, let's go I times I, so we don't forget that, I squared. And then 18 times 8, that comes out to 144, so that actually works out pretty good because it's 12. So in the notes, I started simplifying and went, oh, look, well, this one turns out really nice because it's 144. So anyhow, I squared, that's negative 1 times 12, or negative 12. And you can see if I just multiplied straight away, I would have gotten root 144, and it would come out positive 12. Again, this math isn't real. This is the correct math. And then here's the same idea, but now we're just involving FOIL. So I think what I thought seemed the easiest way, and you could simplify first or not. To me, I just went with, I'm going to write the I out front, and then I'll kind of deal with simplifying the radicals after I've done the FOIL. And you could do it before or after. It works both ways. But we do need to get that into I notation. So I rewrote it like that. And now I'll do out my FOIL. So if I have a negative 2 for negative 10, and on the outside I'm going to get minus 5I root 50. On the inside I'm going to get minus 2I root 18. And then here on the last I'll get positive and negative, so negative I squared. And then 18 times 50 is 900, which actually ends up working out pretty good. And then here, so this is negative 10 minus 5I 50. This is going to be, I'm going to think of this as 25 times 2 here in a second. And then I'll do a step with that. 2I, I'm going to think of that 18 as 9 times 2 in just a second. I squared, that's negative 1, so negative and negative, so I'm going to rewrite that as a plus from there, and then square root 900 is 30, so we can get that part together. And then on the next line, we could do negative 10 and 30, so it's going to be, because those are like terms, so that'll be 20, minus 5I, square root 25 would bring out a 5, root 2. Here we'd have minus 2, square root 9 brings out a 3, root 2. Remember that went with this. And now cleaning that up, 5 and 5 are 25, I root 2, and minus 6, I root 2. Okay, and then combining like terms, I'm just going minus 25 minus 6 for minus 31.